Spiros Sipsas from Chulalongkorn University, Bangkok. Spiros and I go back to APCTP days, my APCTP days in 2013 to 2015, when we were postdoc there in Korea. And we worked together on different sets of problems. Out of them, we managed to publish one paper. We also worked on some in-body simulation codes in cosmology, which we are still pursuing, as that project did not end up the way we wanted it to end up because of certain physics problem like cell crossing singularities. Okay, but I do not want to go on those in detail. But to introduce Spiros, he works on cosmology mainly, but from the angle of the high energy physics. He mainly works on the early universe inflation, but he works from the quantum field theory and the high energy physics point of view. Spiros works on the 2-point and 3-point correlation and the higher point correlation function of the cosmic random fields, so for example primordial perturbations. And today he is going to talk about statistics of cosmic random fields. So without further ado, let me give the stage to Spiros. Spiros.
All right. So thanks a lot, Dheeraj. It's a great pleasure to be here. So I will talk about statistics. As Dheeraj said, this is about correlation functions of primordial fields. Not necessarily 2-point or 3-point, but any point. So, I mean, for now, these words might mean nothing to you if you're not a cosmologist, but I promise that by the end of the introduction, you will all understand at least what that means. Yeah. So since this is a colloquium, I will try to be a bit pedantic in the introduction. I will have very simple notions, but when I actually talk about statistics, then I will get a bit technical. If you fall asleep, that's your problem. Okay, so let me start with an introduction. So what and why? I mean, why do we care about inflation? So what I'm going to say is in the context of inflation. So let me spend some time to tell you what is inflation and why do we need it. All right, so let me start with a simple fun experiment. Yeah, let's consider just a chain of 3 points, one-dimensional. And I want to study its evolution, but its evolution has a very special characteristic. Yeah, in each time step, I add 1 point between every 2. Yeah, and what I want to study now is the velocity with which 1 point moves further from another. Yeah, so you can play this game. It's super simple. You can calculate the velocity of any point going further from any other point, and you will see that it's always proportional to the distance between the 2 points. So if you want to calculate the velocity with which this blue point moves away from this red point as the time goes by, you will find that it is proportional to 1, because the initial distance is 1. Yeah? If you want to calculate the velocity that this guy moves away from that guy, you will find that it is proportional to 2, because the initial distance is 2 units. Yeah? So this tells you that if you plot the velocities and the distances of the points, you will always find that they fall on top of this line. Yeah, that's a very simple toy model, but it is a toy model of the real world. Yeah, because if you really now observe faraway galaxies and measure their velocities, and you plot the velocities against the distances, you will find that it is just a straight line that this law follows. Yeah, exactly as we found in this toy model. So this is our actual data. So as I said, these are the velocities of galaxies plotted against the distance from us. Yes, and now we can interpret this. We know what that means. It means that the universe is expanding, and it is expanding exactly in that way. Yeah. So if these points you consider that there are galaxies, in every time step, space-time is generated between us and the galaxies far away from us. So we see them going away from us like we are at the center of a balloon. But this experiment tells you exactly that we don't have any special position. Yeah. No matter where you sit, you will see that all the rest move away from you. You sit here, you will see that this and that moves away with this speed. You sit here, you see that these two move away. It doesn't matter where you sit. Yeah. So this toy model captures the reality of this graph, and the interpretation of this data set is that the universe is expanding. Yeah, space-time is expanding. It's fun to note that this observation was originally due to Hubble, so this is called the Hubble's law. Hubble made these observations in 1930, so he had the telescopes that he had, he couldn't observe galaxies very far away. So he observed galaxies 10 megaparsec away from us, and he measured the velocities and he found that law, and he said, look, that's a universal law. And now 100 years later we still fall on top of that, the extension of that line. Yeah. All right, so now if the universe is expanding, now you can think logically that if you go towards the past, well, it was shrinking, right? So there must be a moment in the past where everything we see around us must have been more or less around the same space. It must have occupied the same space. And this is what we call essentially the Big Bang. Yeah? So when in the far past, when everything that we see around us was more or less occupying the same small volume, energies were very high, and this is where the universe starts, according to the standard cosmological model. So these are just words, but you can just solve Einstein's gravitational theory, general relativity. We know what the universe contains. It contains photons, right? It contains radiation, relativistic particles. It contains dark matter, or non-relativistic matter. I mean, that's dark matter and us and luminous matter. Anyway, non-relativistic matter, and it contains what we call dark energy. So this is the right-hand side. This is the stress energy tensor. If you want, this is QED, QCD, weak interactions, and that part is gravity. And this is the theory that we know. So if you model these things with the standard QFT, then you will end up with a space-time that follows more or less this profile. Yeah? And you have to cut it at some point because you don't know what happens below that, because you hit some quantum gravity regime. When the energies that you're talking about hit the Planck scale, yeah? Then gravity breaks down, so this theory breaks down, so you have to cut it off. So this is the understanding we currently have about the universe. So let's see what happens. So you start with some very hot and very dense region, yeah? It's so hot and so dense that first of all the particles are relativistic, right? Because the mass doesn't matter, since you have so much energy around. It doesn't matter if it's massive or not. It's just relativistic. So this is a dominated is an era dominated by radiation, relativistic radiation. And the energies are so big that nothing can stay close to anything else. Yeah, you cannot form atoms, you cannot form anything, because the kinetic energy of particles is so big that it wins over any binding energy. So this is just a soup of elementary relativistic particles, which means that when photons travel, they scatter off charged particles. Yeah, so if a photon here travels, and very soon it will encounter some charged particle, an electron, for example, and will scatter. So the mean free path of photons is very small compared to the radius of this soup of particles. Yeah, so it's an opaque space. Nothing travels. Now you put radiation-dominated T mu nu here, and it tells you that the space-time will start expanding with a certain law. So if space-time expands, then energies drop. Just a moment. And if energy, I mean the volume, the volume grows, so the densities drop. So energies and temperatures drop. So at some point, particles become relativistic. Right? Massive particles will become non-relativistic. And this is where the non-relativistic matter-dominated era starts. Yeah. But when this happens, something else also happens, which is very important. Now, the energy drops so much, which is below the binding energy of hydrogen. Yeah. So at some point, as an electron travels close to a proton, it will be captured by the proton, and it will form a hydrogen atom. And hydrogen atoms are important because they are neutral structures. Yeah. So now a photon passing by a hydrogen atom will not care. Yeah, it will pass by unless it has the wavelength of the hydrogen. But this is only a subset of radiation. So from that point onwards, radiation starts traveling free. It is free streaming. Yeah, and this radiation reaches us right now from everywhere in space. Yeah, so at some point onwards, radiation, the universe becomes transparent. So radiation starts traveling without interacting with anything and is reaching us as we speak. And later there is the piece where dark energy dominates. We will not care about that. So these photons that start traveling from the early universe towards us is exactly what we call the cosmic microwave background. And this is an actual measurement. Yeah? So these guys with this silly telescope, they measured in 1965 background radiation coming from everywhere in the universe. Yeah? And this is more or less the explanation. It is when photons start free streaming and reaching us right now. So this was a great triumph of our understanding of physics at that point. But it already poses a big challenge. It poses a very big challenge with respect to this evolution here. So let me now talk a bit about why this picture has a very serious problem in it. Yeah? So first of all, let me say that there is a notion of a horizon in our universe, and it's very simple to understand. Yeah? So since when we were kids, we were told, when you look at the stars, you see the past. Yeah? Oh, when you look at faraway galaxies, you see the past. Well, that means that you cannot see infinitely far, right? Because the light, in order to reach you, requires a finite amount of time. So you can only see 14 billion light years away, because this is the age of the universe. Yeah. So the universe has a horizon. It has many horizons, but one of them is what we call the observable universe. Yeah. It means the maximal distance that can exchange information between the lifetime of the universe. So now let's go back to this picture and try to interpret it. So this is a map of the sky. Yeah. So angular distances here correspond to distances in the sky, linear distances. So this thing here tells you that the CMB that you watch coming from everywhere is a black body with a very specific temperature. It corresponds to a black body with a temperature which is 2.7 Kelvin. Yeah. And it tells you that all the points in the universe that you see have the same temperature. Yeah. Which means that at some point in the past they have to be in thermal equilibrium, right? Because there's no reason why a point there and a point anti-diametrically far can have the same temperature. It's only when they talk to each other. And in order to talk to each other, it means that they should have the time to talk to each other within the lifetime of our universe. Yeah? All right, so let's now put things into GR. Suppose we take this CMB and we take 2 points that correspond to the length of the observable universe right now. Yeah? This is what we call the horizon, h of t. And suppose that we put that in GR and we run it backwards. And we see that it has some evolution. I told you before that when we go forward in time, the universe expands. So we go backward in time, it shrinks. Yeah? And it shrinks according to a very specific law. That's GR. And now you take a length scale close to the horizon, a random length scale, and you run it again backwards, and you see that it shrinks, but with a different law. Yeah? And it so happens that very soon, this blue line, which is the length scale, falls outside the horizon. Yeah? Practically what that means is that most of the points in this observable thing didn't have the time to talk to each other in 14 billion years since the birth of the universe. Yeah? So this is a big conundrum. Yeah? Why, if they don't talk to each other, how is it possible to have the same temperature? And in order to resolve this, one way to do it is to change the dynamics. Yeah? To assume that, okay, the dynamics that I draw here, this cannot be true. There must be another component here that changes the picture, and the picture changes according to that. It must be such that this yellow line stays the same, stops shrinking, but now the blue line starts shrinking exponentially fast, so it runs at the end inside the horizon. And this is exactly what we call inflation. Inflation, because now if we run it forward, you see that things start here and they inflate, they fall outside the horizon, and then they follow their standard evolution, but they have already talked. They were in causal contact, inflation threw them away of the horizon, and they came back at a later point and they formed the CMB. So this is why we think they were uncorrelated, but in reality they were not. They were correlated at some point. Yeah. So this is the solution to the conundrum of the standard model, and this is what cosmic inflation does. So you have an initial period of exponential expansion, and then from here onwards, this is the same evolution as that. Yeah. Okay, so inflation is an integral part of lambda CDM. Lambda CDM starts for lambda starts for dark energy, and cold dark matter for dark matter, and radiation is a small component. So inflation now you add to the lambda CDM, and this is the most up-to-date theory we have of the early universe, of the whole universe, yeah, of the evolution of the universe. Okay, so that was the introduction of what is inflation and why it is important to talk about inflation. Yeah. But as I told you already here, this picture here is very homogeneous. Yeah, it's all green. But if you look around you, the space that we live in is very inhomogeneous, right? Starting from this very room. I mean, there's me, there's empty space, and then there is you. It's very inhomogeneous. There is the Earth, then there is nothing, then there is the sun, and then there is a galaxy and nothing and another galaxy. Yeah, it's a very inhomogeneous space. But this is quite homogeneous. So we need somehow to generate some inhomogeneities, yeah? Because if inflation, if the story is like we said, okay, inflation, inflates space-time, it throws everything away, all the densities drop. So at the end of inflation, you have an empty space cold with nothing inside. But this is not a nice initial condition, right? It has to have some small inhomogeneities that can give birth to what we see around us. So let's see now how you get those inhomogeneities, and this is the second part of the introduction. Yeah. All right. So let's realize somehow inflation. Yeah. So I will show you what form this has to have in order for this behavior of space-time to be achieved. So the simplest thing you can do is put there a scalar field, like the Higgs field, for example, yeah, and give it a specific potential. Yeah, the potential that you want to have is something that is very flat for some time, and then it starts falling into a dip, into a minimum. Yeah. So now, if you put a homogeneous field, if you start this homogeneous field along this plateau, and you give the plateau a small inclination, you cannot see it here, but it has to have a small inclination. What will happen is that this scalar homogeneous field will start rolling slowly down this slope until it reaches this point here, and then it will start fastly falling into the dip. The point is that if you put this picture as an energy momentum tensor into general relativity, it will tell you that as long as the field is in the plateau, the solution of GR is de Sitter space, yeah? Which is a space that inflates, which is exactly what you want. Yeah? Okay, and when this field, the inflaton, let's say, hits this value here, inflation stops and another dynamic starts. Yeah, but this point here is what we need for inflation. All right, so we have a homogeneous field, but any field can undergo quantum fluctuations. Yeah. So let's insert now some quantum fluctuation. Yeah, the quantum fluctuation, if this is homogeneous, the quantum fluctuation can be anything. It can be space-time dependent. It's just small. Yeah. Now, if you add a quantum fluctuation in this picture, what it practically means? It means that if the field, if this ball is the background, is the phi 0. If it is at this value, this is a random process that you can jump either this way or that way. Yeah. If you jump forward, you are closer to the end of inflation, right? So at the space-time point that you jump forward randomly, you inflate less because you are approaching the end of inflation, right? You remove some period of inflation from this point. If you jump backwards, you add inflation, right? Because you jump further away from the end. So this process, I will show you in the next slide, it generates temperature anisotropies, and let's see why. It's fun to see how it does it. So this is exactly what I said before. Take this potential, and let's do another experiment. Let's part space-time, a space-time neighborhood into 4 points, and let's study in these 4 points some realization of this quantum jump. Yeah. So at this point, the field jumps forward. Yeah, with a plus. it means that this point inflates less than the average, than the background. Yeah? So there is this lattice gets deformed like that. Yeah? It shrinks with respect to the background. So everything inflates, but this point inflates less because here the field jumps forward towards the end. So it gets deformed, space-time gets deformed in that fashion. In that point, same happens. This is just a random realization of this jump. Yeah? So in this point, it jumps forward. In this point, it jumps forward. In that point, forward. But in that point, backward. Just a random realization. Yeah? So in the point that it jumps backward, it will start. It will move away from the end in inflation. So it will inflate more than the average. So space-time will be deformed in that fashion. It will the volume will be bigger with respect to the background. So now, when later matter goes and sits on top of this locally deformed space-time, when photons start, traveling through the universe, when a photon finds this deformed volume, it will form an overdensity. Yeah, and photons passing through a potential well, it's an overdensity, a gravitational overdensity, will lose some energy. Yeah, so we will perceive them as a bit colder than the average. And photons that pass from this kind of spatial deformation, they will gain some energy with respect to the background. Yeah, so we'll perceive them as cold, as hot spots. So this is exactly okay. So this is a way to show this thing in GR. It doesn't matter. So this is the picture that you get at the very end of the day. So this is the real CMB picture that we measured from 91 and afterwards. Yeah. So this picture was the picture that we measured in 1965 with this sloppy telescope, but now we measured in 2018 with this, the Planck satellite. Resolution has increased, so we saw that it's not exactly uniform, but it contains small temperature fluctuations. And the theory of inflation explains these fluctuations exactly as quantum mechanical jumps of the field in the early universe. Yeah. So this is a picture, but just to show you that it is actual data. So here is the data. So Darius knows that much better than me. So you can go to the Planck Legacy Archive. You can download their data and you can open them somehow. And these are the actual data. So these are pixels in this picture here. And each pixel contains a number. And each number corresponds to temperature, temperature fluctuation around the background. Yeah, and it is exactly what we saw. And not only we explain what we see in the CMB, but we also explain what we see around us, because these inhomogeneities, space-time inhomogeneities that gave rise to CMB anisotropies, later, when we are, so as I said, CMB is generated at this point where the matter and the radiation are almost the same in density, but later in the evolution, these same inhomogeneities give rise to galactic cosmic structures like galaxies and clusters of galaxies. Yeah? So you have a small inhomogeneity, then matters flows into this area, and if it is deformed, shrinked, then it forms an overdensity and it starts gravitating and pulls matter around it, and it forms a structure which is a galaxy. So not only we explain the CMB, but we also explain the cosmic web with that kind of theory. Of course, let me tell you that this is just a theory. Yeah, it doesn't mean that this is exactly what happened, but it is a narrative. It is an explanation of what we see. There are other models that try to explain that, like bouncing cosmology or other stuff. But I think inflation is one of the best because it gives very natural explanation of that stuff. And so this is a recap of what we discussed up to now. So you have quantum fluctuations of the primordial matter. Let's call that the inflaton. These quantum fluctuations create localized spatial deformations because of the quantum jumps. And then later, where matter goes and sits on top of this deformed space-time, you see fluctuations of matter, be that radiation in the CMB or inhomogeneities in dark matter, which means galaxies, yeah, and classes of galaxies. So that's a picture. Now this is where the statistics come in. So the statistics of these inhomogeneities are first observable, yeah? Because we can count. We can take the CMB. We can count how many cold spots we see, how many hot spots we see. We draw a histogram, and that's it. That's the statistics. So first of all, it is observable, and second, it contains all the information of the primordial dynamics. Yeah, I will show you. This will be the main focus now: how to extract information of the statistics. And let me also highlight the point: why do we have statistics? Well, because it's a quantum process. So the quantumness, if you want, of this process here translates into a statistical set of temperature fluctuations. So the CMB, and if you want, the whole universe, according to this narrative, is a huge scale system where you can really see quantum effects. Yeah, where quantum now has nothing to do with h bar. Yeah, it's just statistics. It's just a statistical field theory. Okay, so that was the introduction. So now I want to focus more on the actual statistics of the CMB and show you how to use them. Yeah. So how can we extract information from some statistics? Yeah. So this is a very crude statement here. Okay, the first line is a crude statement, but it kind of makes sense. Yeah, I mean, this is the path integral formulation. It tells you that the probability density function more or less is e to the action. So if you know the action, then you know the probability distribution function. And an example is that if you have, for example, a free theory, which is a quadratic action, you have a Gaussian model. Yeah, you have a Gaussian path integral. Good. So if you reverse now the statement, non-Gaussianity in the statistics that you measure is a very clear smoking gun signature of non-trivial dynamics. Yeah, because if you have non-Gaussian PDF, it means that your action there is not quadratic, which means it contains interactions. Yeah, so you can use this statistic that you measure to infer what was the dynamics of inflation, and this is physics on scales that we will never be able to probe with LHC or whatever comes next. Yeah. So it's a real probe into very high energy physics. All right, and this is just an example of what I mean by non-Gaussian. This is just one choice. Yeah, there are many infinite ways to deform a PDF, but this is one that I will show you. So you have a Gaussian which is modulated by a cosine, if you want, or by some wiggly thing. Here it's very exaggerated, of course, but just to make the point. All right, so this part will be a bit more technical, but I think we'll manage. So the mechanism now I want to use in order to generate these statistics is in the context of multi-field inflation. So what means multi-field inflation? So I showed you the simplest example here of inflation, where you have just one field with a specific potential. But now I want to think that, look, why have only one field? We can have two fields or more fields. Why? Well, because if you talk about, you know, the early universe and the quantum gravity and whatever, and string theory and supergravity, then it's quite natural to have more than 1 degrees of freedom active during this this phase. Yeah. So I want to see what if we have 2 degrees of freedom active. Yeah. What would that do? So this is what I mean by multi-field inflation. And now, instead of having one potential which is one-dimensional and it has a plateau and then a dip, I have a very complicated random surface, yeah, a random potential. The only requirement that I want is that this potential contains this red line, and this red line is flat. Yeah, exactly because I said that this plateau here has to be flat for inflation to work. In this complicated landscape, I also want to have a flat direction. But flat doesn't mean that it cannot bend. It can bend. Yeah, it can have turns. Flat means that as I go along the trajectory, I don't find bumps or dips, but I can turn. Yeah, there's no problem in turning. So the building block of this trajectory is either a flat line, a direct line, or a turn. Yeah, so this is just a turn along this path. And let's study now what the theory of perturbations is along this trajectory. So you need to define two perturbations. One is along the trajectory, and the other is transverse to the trajectory, so 2 degrees of freedom. And the important thing is that these perturbations are coupled by the turn. Yeah, and it's easy to understand why. Because when you travel on a straight line, nothing happens in the transverse. But when you turn, you climb up a bit the wall. Yeah, so you can consider it as centrifugal force. So you excite the transfer perturbation, which means that the turn couples the two. Yeah. So the theory that you end up with is just that. It's very easy to guess. So you need to write down the kinetic terms. Psi is the transverse direction. It can have some interactions. This is the potential. And the coupling now, which is contained in this weird kinetic term, is just bilinear coupling of zeta dot and psi. Yeah? So this is a universal theory of perturbations at quadratic order. Yeah? Right, now you see that psi is nonlinear because it has a potential. So it will have some non-Gaussian statistics. And due to this coupling there, in the kinetic term, it will transfer the statistics to zeta, and zeta is what creates the CMB. Yeah, so I will see in the CMB the statistics of the second guy, which is psi there. I denote that psi. Psi can be whatever. It can be an axion. Yeah, it can be some field that has dynamics, but it couples to inflation due to some complicated potential. And I want to see how this gets imprinted in the statistics of the CMB. So, okay, that's a heavy slide, but it's not hard to follow. So what I want to do is to compute an endpoint correlation function of zeta, and then from this endpoint correlation function of zeta, deduce a PDF of zeta. This is not very easy to do if your theory is arbitrary, but if your theory is close to Gaussian, then you can do it. Yeah. So how do you compute an endpoint for correlation function of fields in an inflating background, which is the zeta space? Well, you have to use this, what is called an in-in formalism, or Schwinger-Keldysh contour, if you're more familiar with that, which means that you sandwich this endpoint correlation function with two exponentials of the Hamiltonian. You expand the exponential and you compute order by order. Yeah. So this is what I've done here. You need an endpoint correlation function. So you need, is there a mouse in this? Yes. You need to compute an endpoint correlation function. So you have n external legs. The only term that will survive from the expansion of the exponential is the one that contains n times this Hamiltonian, which is the Hamiltonian of the coupling. So you have n times this thing. You need to couple the zeta external with the zeta's internal. This leaves you with n psi's, and the n psi's will couple with a term in the expansion of this potential with n psi's. And then you will be left with whatever else lies there. So the terms that couple between them, they're contracted between them, form loops in this diagrammatic representation. So each endpoint correlation function is a series expansion, is a Taylor series, and the Taylor series comes from the Taylor series expansion of this Hamiltonian. The good thing is that you can resum this Taylor series back. Yeah? And if you resum it back, you will see that each endpoint correlation function gets deformed by the whole potential. So you can sum all these diagrams and get a closed form answer for the endpoint correlation function that contains the potential that you started with. If you do all that, then you can compute what PDF would give me these correlation functions that I computed, and you find that the PDF is given by that form. It has a part which is Gaussian, because you are in a quadratic theory, and zeta has a quadratic part. And it has a non-Gaussian deformation, this delta. And this non-Gaussian deformation is given by some operator acting on the potential. Yeah? With some kernel, it doesn't matter. So there you go. You computed how an interacting field, psi, transfers its nonlinearity to zeta, and zeta is the thing that creates the CMB fluctuations. Yeah. So you have this connection. Now, if you have this knowledge, you can play the opposite game. Yeah. You can look at the CMB. You can try to measure rho and reconstruct V. Yeah. The dynamics during inflation. So in order to do that, you can just expand. You expand this delta there in Hermite polynomials. Yeah? You can also expand the potential in Hermite polynomials. So this is what we do there. And using Hermite identities, you can see that these coefficients of the two expansions are the same. Yeah? So if you manage to measure AN, this coefficient, you automatically know Bn. And if you know Bn, you can reconstruct the potential. Yeah? So this is what we did here. These are the coefficients An. So you expand this PDF in Hermite polynomials, and you just compute. So you compute the PDF from the data, and then you compute Hermite moments. Yeah? And this gives you the number An. Once you know Ans, which is these are the Ans, you can just simply plug them in here and reconstruct this potential. Yeah? So these are the Ans. So these contours mean that whatever you find inside here is compatible with 0. It's not of statistical significance, and of course everything is compatible with 0. But you see that the 4-point function, which is given by that, is non-zero, but still it's compatible with 0 statistically. But if you take it to face value, it means that the 4 component is non-zero, and that would give you a quartic potential. For example, you can say that this is the Higgs field, right? That is coupled to the inflaton. So you reconstruct a potential for this field psi, and this is an example where you use observations to infer a potential for some field during inflation. You see that also this potential, which is this blue line, also lies inside a contour, and this contour again means that it is compatible with 0, because this contour corresponds to these contours here. Yeah? The important thing here is not the results, but is the mechanism. Yeah? The important thing here is this discussion here, this slide and that slide. Once you have better data, these contours will shrink, and then if you find a point outside this contour which is statistically significant, then you can say, okay, I will run this program, and here is the potential. Yeah? Let me make a point why these contours appear here. It's very easy to understand from this example that we played. Right, so here, this is a random realization of a very Gaussian process. But the result, you see, it's highly non-Gaussian, right? Because if it were Gaussian, it would have 1 plus, 1 plus, 1 minus, 1 minus. But just because it is one realization of a random process, the result, of course, is not Gaussian. In order to find something Gaussian here, you would have to run this program an infinite amount of times. Yeah, on average, it's Gaussian. What? Exactly. But the point here is that first of all, our universe comes once. Yeah, there's no, you cannot replicate it. It is what it is. And it doesn't contain infinite points. Yeah, it's a finite amount of data that we have. So these contours here tell you that you only have one realization. It's just variance, cosmic variance. It tells you that you will never see something Gaussian. It will always be non-Gaussian because it's just one realization. If you have an infinite amount of data, then these contours would shrink to 0. And what lies outside this contour, this you can really attribute to primordial origins, to dynamics. Yeah. So these contours are just statistics, and the things that lie outside this contour, these are real dynamics. But you see here, no point lies outside this contour, yeah? Which means that what you observe is very close to Gaussian. But the important thing is the mechanism, that whenever you have something, you can use this program and attribute it to some potential. Okay. So I will also talk a bit about something else, but not that much, because it's also related to statistics and non-perturbative physics. Yeah. So let me now do something. So the other part I want to mention is statistics of extreme fluctuations, and this comes to primordial black holes. Yeah. So let me first tell you what is a primordial black hole. So let's go back to here. Yeah. So you create a special deformation of space-time, yeah? And we said that then photons pass and they create temperature anisotropies, yeah? And we measure the CMB, and that distribution is more or less Gaussian. Yeah. Now we can forget about the non-Gaussian part. Let's focus on Gaussian theory and these deformations. Okay, so you have a Gaussian distribution, and it has some variance. Yeah, sigma squared. And you know that this sigma squared is 10 to the minus 9 or something, because you measure it in the CMB. So this gives you a typical amplitude of this deformation, which is, let's say, 10 to the minus 5, yeah, or 10 to the minus 4, whatever. Fine, this is what you measure from the CMB. Now you say the following. Imagine that this deformation is super big. Yeah? So in the CMB we see it small, but the CMB only tells you what happens in one certain scale, large scales. Imagine now that you have a deformation which is sigma, it's the amplitude of this deformation is 10 to the minus 1. What would happen then? Well, you put it into GR, and if you have such a big deformation of space-time, you put matter in it, it collapses and creates a black hole. Yeah? So this is a primordial black hole as opposed to an astrophysical black hole, because astrophysical black holes, they are stars, they die, if they are mass enough, they collapse. But primordial black holes have an origin in primordial fluctuations. That's why we call them primordial. Right, so why now do we care about that? Because it's an excellent candidate of dark matter. Yeah? So if you have black holes like that form in the early universe, they were never luminous matter. They are a perfect candidate for black matter because it's just a fluid of non-interacting, sparse, heavy, non-relativistic particles, which is exactly what dark matter it is. Yeah? Since we don't know what it is, it might just be primordial black holes. So this is why we're interested in primordial black holes. But I want to show that they are also very interesting theoretically. Okay, so now there is a question here. What is the probability? If you have a Gaussian distribution like that, what is the probability to get a fluctuation of that size? Well, it's absolutely 0, yeah? Because this is 3 or 1,000 times bigger, so the probability that you get that is e to the minus 1,000 squared, yeah? It's absolutely 0. So you need two things in order to be able to generate primordial black holes. One thing is to say that, look, as time goes by, something happens, and this variance gets very enhanced. How much? 1,000 times more. Yeah, and with that Gaussian distribution, then it's quite typical to get this fluctuation. So this is one way to generate primordial black holes. And the other way to generate primordial black holes, let me just show it here. Okay, so this is what I drew there. So this is a Gaussian distribution at some time where scales that the CMB cares about are formed. So CMB is Gaussian. But as time goes by, something happens and the variance of this Gaussian gets stretched. Yeah, so at the end you end up with a Gaussian distribution again, but with a huge variance. And here it's quite typical to have large fluctuations. Yeah, so this is a model. It's not a model. I haven't said how to get that. It's just a statement. So let's. I just want to say that the model that I used before to show you how you can get non-Gaussianity in the CMB, you can also generate primordial black holes. The only thing to note, to play around, is that this coupling alpha there, if it is small, then you can generate non-Gaussianity, but not extreme fluctuations. If it is very large, you can generate extreme fluctuations, because this coupling is involved in the power spectrum. Yeah, so you can play around with this model. You can actually solve it exactly. These are the equations of motion for the model I showed you. You can have alpha very big, and you can solve the model exactly. And what you see if you compute the power spectrum is this enhancement. Yeah. So that's one way to generate primordial black holes. But the other way that I want to focus on, this is my last slide, by the way, is this. So one way is to increase the variance, but the other way is to mess with the tail. Yeah, because if you mess with the tail, it means that you increase the probability of very large fluctuations. And this is very nice, because it gives you an incentive to study non-perturbative effects. Yeah? And why is this non-perturbative? Well, it's simply to see, because suppose you have a phi to the 4. Yeah? You write the equation of motion and you get the Klein-Gordon plus blah 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 plus a potential which is phi cubed with a coupling, G. So that's your equation. Yeah? And you say now, okay, I will consider G small and I will do perturbation theory. And this is what we do with Feynman diagrams. Yeah? We consider a small coupling expansion. But if your initial condition is huge, then this theory is not linear anymore, right? It doesn't matter how weakly coupled it is. If the field amplitude is huge, then you are left with a theory which somehow you have to solve non-perturbatively. So this is an incentive to study non-perturbative physics with actual observations. Yeah. Well, we haven't observed any primordial black hole yet, but if we ever do, and then we can reconstruct this mass function, this PDF, the distribution function of black holes, and this would really give you, it might give you something like that, and it's an incentive to study non-perturbative physics. So one way to do non-perturbative physics is this, the thing that I already showed you, I mean the method. So it has to do with resummations of Feynman diagrams. It is a good question if there are other non-perturbative methods. And people in QCD and quark gluon plasma would know much more ways to do non-perturbative stuff than me. But this is a nice setup to apply nonlinear methods and non-perturbative methods. So this is what I wanted to say, more or less, that statistics of fluctuations are related with high energy physics and non-perturbative physics, and all this you can observe just by looking at the sky. So we said that inflation is a necessary gradient of the standard cosmological model because it solves several problems. The predictions of inflation have been confirmed, but that does not mean that inflation has been confirmed. Yeah, it just explains what we see. In both CMB and LSS, LSS means large-scale structure, which is the set of galaxies and stuff that we observe. And the important part is that the statistics of all these fluctuations, we didn't talk about galaxies or gravitational waves, but you can also play this game. The statistics of CMB and primordial black holes contains the information of physics at extreme conditions, either at extremely high energies or at extreme amplitudes. Yeah? And what we need to verify all that is, first of all, more data, because then we can reduce the noise in the data, so we can have more definite measurements. Better estimators, how to estimate PDFs, because this is one way I showed. Compute endpoint correlation functions, but it is not the only way. Yeah, there are other estimators of statistics, not only endpoint correlation function. And finally, better understanding, right? To improve statements like that, like this one. Yeah, we need further understanding to be able to write such formulas in a non-perturbative manner. Exactly because when we talk about primordial black holes, we are interested in non-perturbative regimes, in tails PDFs. And I will leave it there.
Yeah, thanks, Spiros, for the brilliant overview of the primordial physics. So now the floor is open for questions. Let's see.
So thanks, Spiros, for this very nice talk. So I had some questions to you. So when you look at the moments, you calculate as a series, right? So all the series are asymptotic series.
Yes.
And of course, when you resum them, you will get non-perturbative physics out of it. That is now a big area of research.
Mm-hmm.
But then here, if your fundamental quantum field theory, how much control do you have on it? Do you know that it is very well controlled? Then
that's a good question, and the answer is very easy: no. But because I mean, this is non-perturbative in one sense, right? It is non-perturbative in the sense that you don't have to truncate the potential, right? You keep the whole potential. You expand in Taylor, and then you are able to resum it back to the. But it's still first order in the potential. Mm-hmm. So you can continue here. And go to second order. So you see that this is lambda to the fourth, and lambda to the fourth is the order of the potential. This is just the first term in the series. The next term would be lambda to the 8. Yeah? And then it will go on and on. So it's non-perturbative in the potential, but it is very perturbative in the coupling of the potential. So this series converges simply because you have a fundamental theory that has a potential. It is a function. Yeah. So you expand it in Taylor, but this Taylor has to converge back to V somehow. But if you want to treat it really quantum mechanically and start inserting higher order operators, yeah, I'm not sure if it will converge to something which is resummable. So yeah.
But in this way of doing things, you can show that the loops can be resummed.
Right. Yes.
And does it have any non-perturbative effects? Like I can see there is an exponential term here.
Right. This is a notion of non-perturbative thing, but in that sense that I mean, it dresses the vertex somehow. It somehow renormalizes the coupling of the vertex with some exponential. This is just the variance of the Gaussian theory, the Gaussian variance. So it is non-perturbative in the sense that that all the derivatives of the potential are there. You don't truncate. It's resummed, but still this is first order in the potential. So I mean, one wild guess would be to take this result and exponentiate it in the potential, so that this is just the first term. Yeah, but nobody. I mean, this is what we're trying to do now, to compute this to second order in the potential and see if there is some pattern between the first order and the second order. But yeah, I'm not sure if it's guaranteed that all this discussion will go through at the second order in the potential. Maybe it does, but.
Then in the next generation experiments that are coming, could you actually make a distinction between different models or different models of inflation? How close should be?
Right, that's a good question. So you know this Event Horizon telescope that took a picture of a black hole, yeah? So how did they do that? They combined all the telescopes in the Earth as if it were one. Yeah, they were looking at the same thing, and then they patched together stuff, and they saw the black hole. So there is an experiment planned which is called CMB Stage 4, and it's more or less is the same concept. So they will use many telescopes which have been independent up to now, but to have the same, they will be treated as one. Yeah, and this promises to increase the resolution by an order of magnitude. So, for example, it promises to shrink this contour. By one order of magnitude. This, yeah. So if this point here is real and not fake, and this contour decreases by an amount, then it will lie outside the contour, and then you will say that, look, non-Gaussianity is there. And there are hints that there is non-Gaussianity, but it always lies between these contours. So if you shrink them, then it will reveal itself. And CMB S4 promises to reduce this contour by a considerable amount, such that this point, for example, would really lie outside, and stuff like that. So it's not only CMB-S4; there are more, but that's the main thing that we wait. And also, I didn't mention here. I also put the word LSS, large-scale structure. You know, for the next 20 years, this will be the main source of data. So you have experiments like Euclid, which is launched in 1 month or something, and LSST, that they will measure distributions of galaxies. And there you have more data than the CMB, but there you have more noise, because gravity is nonlinear, so it gives you non-Gaussianity anyway. So you have to remove that. You have to have very good knowledge of the background, and then they are very far away objects, so they're hard to measure. But this will be the main data input. And this also contains information about non-Gaussianity, and this also promises to reduce these contours by some considerable amount. So I guess if you combine everything, well, in the next 25 years, probably we might have some answer. Maybe Dirac already has an answer.
And the last question was regarding your last slide. You had this non-Gaussian ETM. So is it that you have to have a second peak or some structure, or you just need a long tail distribution?
Yes, no, a long tail distribution.
You need a long tail distribution.
Of course, yes. No, this is just a drawing.
So if you have long tail distributions, then the rare fluctuations become important, though it is rare.
Exactly, yes. You need somehow just lift the tail. This is the Gaussian. You need to somehow say that the real tail goes like that. Maybe it goes like that instead of like that. So if you find, and there are works that claim to have computed things like that. So you just need to lift the tail. Yes.
Thank you very much.
Thank you.
Any other questions? No? If not, let's thank Spiros again.